So welcome back everyone to the start of part 4 of this 5-part series on mathematical modeling of organic contaminants and subsurface remediation. In this section we'll look at some case modeling studies on diesel and gasoline spills. So this first application, we're interested in simulating the effects of gasoline additives on benzene persistence. So it's an example of multi-component biodegradation of gasoline components in a porous medium. So we're looking at effects of ethanol here, and as you are familiar with, we're adding more and more ethanol to gasoline these days to help the efficiency of the combustion and to perhaps minimize environmental effects. But one issue of ethanol is that it might consume some electron acceptors and leave the remaining benzene toluene components perhaps more persistent. So here's an example. We'll use this example of ethanol and gasoline as an example of how to set up a multi-component model. So first we need to define our conceptual model and boundaries as we've done in the previous lectures. And here we'll be simulating a dissolving non-aqueous phase liquid of gasoline, residual phase liquid here at the water table. We have some recharge across the top and flow generally from left to right out this right boundary here. Some dispersivities will apply based on the system scale, and this will be done in 3D with 30,000 nodes. So here's our formulation for the dual Monod biodegradation term as we've seen in the previous lectures. So we need to define some of these rate terms, including this maximum rate and these half utilization rates for both the substrates, for each substrate, and for the electron acceptors. So here is our component mix. We'll be simulating 4 components of gasoline, benzene, TEX, that's toluene, ethylbenzene, and xylene, will be grouped into one component. All the other components, the heavier, less soluble components, as well as ethanol. So these are 4 components making up the total mass of our gasoline source. So we need to define the mole fractions of each component, and we'll be comparing 2 scenarios here, one with gasoline only and one with gasoline plus ethanol. For each of these components, we will define a retardation term and a maximum biodegradation rate. For this simulation, for these 2 simulations, the ethanol and no ethanol case, we'll be assuming a background oxygen concentration of about 3.8 milligrams per liter, and there's only oxygen in this case as an electron acceptor, a background microbial population of 3, and half utilization rates of 2, and a microbial yield coefficient of 0.5. So one of the first things we should look at in the transport model is an understanding of what's coming out the source. We're going to treat the source as a dissolving Napo phase, dissolving under Raoult's law. So just plotting this concentration coming off the source as a function of time. We have our 4 components, and we can label them as ethanol here. Ethanol is very soluble, high concentration, but very short duration. It's completely miscible and dissolves rapidly from the source zone. The next to dissolve completely would be benzene, followed by the TEX pseudo component and all the others. You notice, for instance, as ethanol dissolves, the mole fractions of the other components, the remaining components, increases slightly. And similarly, as benzene completely dissolves, the mole fraction of the other remaining 2 components will increase. So this is an important concept to understand in interpreting the plumes, the aqueous plumes, is the behavior of the source zone. So here's our base case gasoline source. So this has no ethanol. So this is after 20 years. We're plotting benzene, TEX, all the remaining components, plus the oxygen consumption. So we see after 20 years, benzene is long since dissolved from the source zone. We have this little aqueous phase residual plume that's going ahead. And TEX, being less soluble and more massive in the source, it's still connected to the source as well as the remaining compounds. Comparing that with exactly the same case, but with ethanol added, we can see after 10, 15, 20 years, now benzene is a bit remaining here, and this is because of the ethanol. This is ethanol after 20 years has consumed more of the oxygen than in just the gasoline alone case. So there's less oxygen available for the benzene to degrade. Now there's more oxygen being depleted here. This is similar to this gasoline-only case, because this is dominated by the consumption by the TEX and the remaining compounds, which really don't really change a lot in the simulation. So this is an example of a multi-component nonlinear transport simulation, and a good application of a model in that we're comparing two scenarios. We're not making any absolute predictions of behavior here. We're looking at a difference in two otherwise identical simulations just with the effect of ethanol. Now, this conceptual model has actually changed. This was done about 10 years ago, but still, at the time, this was very useful to help in our planning for future field experiments and just basic understanding of this type of behavior. Now, numerical models are essentially expressions of mass balance at each element. So we can keep track of the mass of each of these components and how much is degrading. And this can be a test of the model and can also help us understand where our mass is going and what processes are consuming the mass more than others. So here, for instance, is the benzene mass plotted as a function of time. And here, just superimposed, we have 3 plumes of benzene, 3 times for the benzene plume. So the source mass, for instance, decreases rapidly just as benzene and is completely dissolved by about 3,000 days. As the source mass dissolves, the aqueous mass, this blue line, increases. But at the same time the aqueous mass is increasing, the biodegraded mass is increasing. So this aqueous phase is actually degrading. So this is the total amount of biodegraded mass. And we have a bit of absorbed phase mass as well. And the sum of these masses, the absorbed, the aqueous, and the biodegraded mass, should give us a total benzene mass. And if mass is conserved, this of course should not change. And these little bumps here, we have some growing mass, and this is an acceptable numerical error. As long as it's small enough compared to our total mass, we can accept a small mass balance error. But otherwise, it's not bad. We're conserving mass here more or less, and we can see that that biodegraded mass is quite important. And in a second application, we'll be looking at diesel fuel dissolution. I guess you can tell this slide's quite old. Look at the price of gasoline, 71 cents a liter. It's about double that now. So we're looking at diesel fuel, and in particular the behavior of diesel fuel with enhanced dissolution. We have this diesel fuel residing at the water table, and specifically with the use of humic acids was one method to propose to enhance the dissolution. So we'll be looking at that. This is based on a dissolution experiment performed at Environment Canada in the late 90s, early 2000s, and we published some papers on this. So this is another example of just how to set up a model. Here's our sand tank experiment. Looking down from the top, we have a head tank system about 5 meters long, and we have some monitoring wells here. This is a completely enclosed sand tank. We have a head tank that's forcing water towards the right, and a purge well pumping out the water here. We have a residual diesel source zone here, and several monitoring wells down gradient. Here's our 3D grid we've developed. We've designed this grid so it's finer around the source zone where our concentration gradients will be highest, and will also be fine near the purge well where our flow gradients and again concentration could be high. So the conceptual model for this diesel dissolution experiment, we've divided our diesel fuel into 8 organic components. So we've got BTEX, that's 4 components, methyl, dimethyl, and trimethyl naphthalene, 3 more components, and then all the other components of diesel make up the 8th component, all the heavier components. And this is a common approach to lump heavier components together. They have lower solubility, and we're mostly interested in these lighter, more soluble, and more toxic compounds. Together with these 8 organics, we're simulating dissolved oxygen and a single microbial population. Now, to add to this, we're adding a humic acid carrier, and the idea here is that the absorption of the contaminant out of the humic acid would enhance its dissolution rate. So here is a plot of the observed naphthalene concentrations at different times, at selected times, 41, 70, 385, and so on. So we can see our diesel fuel is dissolving, and there's a spike here. This humic acid was added after 50 days, so we get this spike in dissolution. And then gradually the source becomes dissolved and degraded. Here are the simulated results at the same times and the same color scale. So peak concentrations of about 1600 micrograms per liter. So again, we get this spike at 70 days. Well, actually at 50 days when humic acid was added to help enhance the dissolution of the source. And then just visually, we can see a good correlation between these plumes. Peak concentrations are well matched, and complete dissolution is well matched. So we can say with confidence that this is a reasonable conceptual model for this scientific experiment. And then, for example, we could go on and apply this model to other sites. A third case study was the case at Borden, looking again at gasoline spills. And I think Jim Barker has covered some of this already. We have some injection wells for dissolved gasoline and some monitoring wells down gradient, all enclosed in a sheet pile area of the porous medium at Borden. So to set this model up, again, we're looking at ethanol in gasoline and an effect of a buoyancy in this case. So here's a vertical section. We've simulated the flow system. We've put boundary conditions on, a fixed head up gradient, fixed head down gradient, so that induces our known flow gradient, applying some recharge across the top. So we get a flow system that's dominantly horizontal. Here's our grid. We can define based on the Peckley number. And here's our source zone. We'll be starting out with a dissolved phase and residual phase gasoline. So we're going to compare three cases here. Basic gasoline with MTBE, an E10, 10% ethanol, and a 95% ethanol case. Here's our grid. So just a quick review of the properties that we need for our model. I won't go through them all. Hydraulic case, typical of Borden, porosity, velocities. Dispersivities, again, very important for reactive transport, and a time step based on the Courant criteria. Our sort of geochemical properties, solubilities, diffusion coefficients, sorption parameters we need to define for each of our components, benzene, tex, all the other components, as well as ethanol. The source zone, we need to define the masses and hence the mole fractions of each component. So again, we'll be comparing these two sources here, just different concentrations of ethanol. So here are the plumes at 100 days. This is from the E10 source, ethanol and benzene, and from the E95 source, ethanol and benzene, all at 100 days. So we can interpret these plumes again. We have to consider what's happening at the source. So here are the source concentrations being plotted right here versus time. So we get these soluble components, MTBE, TBA, and ethanol dissolving quite rapidly. And basically, all the other components residing are taking much longer to dissolve from the source zone. You can start to see an effect here of buoyancy. This was another area of interest for this simulation. Ethanol being lighter than water, we might expect it to rise, and in fact, this was important for at least the E95 plumes, not so much for the E10. But to distinguish a possible buoyancy effect from natural changes in the flow system, we decided to run this simulation for several scenarios of different permeability fields based on the statistics for the Borden site. So here are the 5 realizations. At the left here are the hydraulic connectivities. So again, in red we have some high K zones, in blue we have some low K zones. These are all based on the Borden statistics, so these are all equally probable realizations. And this is the flow system on the right here based on these different connectivities. So we run the transport model for each of these flow systems and look at the behavior of the plumes in these flow systems and see if we can still see density or buoyancy effects. So here's one result from one of the realizations. Here's the hydraulic connectivity field. Here's the ethanol plume at 10 days, 50 days, and 100 days. So we can see a very complicated type of almost like fingering effect coming out because of the connectivity changes, and also somewhat due to the buoyancy of ethanol. This being the E95 case, where a very high ethanol concentration. So comparing this realization at 50 days and 100 days, we can gain insight into the properties and the behavior of the plume. So here's benzene, toluene, and xylene at 50 days, and the other components at 50 days, TMB, ethanol, and all the other components. So again, we can see that the soluble components like ethanol have detached completely from the source, whereas the other less soluble components are still dissolving at 50 days, and the bulk, being even more retarded and less soluble, is very close to the source zone. And after 100 days, we can see the evolution over time. Benzene has now, looks like, dissolved completely from the source, whereas toluene and xylenes perhaps are still dissolving. TMB still dissolving, and ethanol evolved further in the bulk. So a simulation, this is a single simulation for one realization, just showing different times and different components. We can gain a lot of insight into what's happening. I have a short video showing the evolution of the ethanol plume in this hydraulic conductivity, this heterogeneous conductivity field. So we can see ethanol evolving, and it's degrading too. It's being biodegraded. In this case, the heterogeneities have a big effect. And so that concludes part 4, and I invite you to return to finish up with part 5. Thank you.